Welcome back. In this video, we're going to give a very brief introduction and overview of what we're going to be talking about in semantic analysis. Let's take a moment to review where we are in our discussion of compilers. So we talked about lexical analysis, and from the point of view of enforcing the language definition, the main job that lexical analysis performs is to detect input strings that have words in them or primitive symbols that aren't part of our language. The next step is parsing, and we finished talking about that too. And again, from the point of view of trying to determine whether a program is well formed or not, or whether it's a valid program, the job of parsing is to detect all the sentences in the language that are ill-formed or that don't have a parse tree. And finally, what we're going to be talking about now, what's going to occupy us for quite a while, is semantic analysis. And this is the last of what are called the front-end phases. So if you think of lexical analysis, parsing, and semantic analysis as being filters that progressively reject more and more input strings until finally you're left, after all three phases have run, with only valid programs to compile, well, semantic analysis is the last line of defense. It's the last one in that pipeline, and its job is to catch all potential remaining errors in a program. Now you might ask yourself, why do we even need a separate semantic analysis phase? And the answer to that is very simple. There are some features of programming languages, some kinds of mistakes you can make, that parsing simply can't catch. Parsing, using context-free grammars, is not expressive enough to describe everything that we're interested in a language definition. So some of these language constructs are not context-free. And the situation here is very, very similar to what it was when we switched from lexical analysis to parsing. Just like not everything could be done with a finite automaton, and we wanted to have something more powerful like context-free grammars to describe additional features of our programming languages, context-free grammars by themselves are also not enough, and there are some additional features beyond those that can't be easily expressed using context-free constructs. So what does semantic analysis actually do? In the case of coolC, it does checks of many different kinds, and that's pretty typical. So here's a list of 6 classes of checks that are done by coolC, and let's just run through them quickly. First, we want to check that all identifiers are declared, and we also have to check that any scope restrictions on those identifiers are observed. The coolC compiler has to do type checking, and this is actually a major function of the semantic analyzer in cool. There are a number of restrictions that come from the object-oriented nature of cool. We have to check that the inheritance relationships between classes make sense. We don't want classes to be redefined. We only want one class definition per class. Similarly, methods should only be defined once within a class. Cool has a number of reserved identifiers, and we have to be careful that those aren't misused. And this is pretty typical. Lots of languages have some reserved identifiers with special rules that have to be followed for those identifiers. And actually, this list is not even complete. There are a number of other restrictions, and we'll be talking about all of those in future videos. The main message here is that a semantic analyzer needs to do quite a few different kinds of checks. These checks will vary with the language. The kinds of checks that coolC does are pretty typical of statically type-checked object-oriented languages, but other families of languages will have different kinds of checks. Welcome back. In this video, we're going to begin our discussion of semantic analysis with the topic of scope. The motivating problem for talking about scope is that we want to be able to match identifier declarations with the uses of those identifiers. We need to know which variable we're talking about when we say variable x, if variable x might have more than one definition in the program. And this is an important static analysis step in most programming languages, including in cool. So here are a couple of examples taken from cool. This definition of y, this declaration of y, that it's a string, will be matched with this use. And so we'll know at this point here that y is supposed to be a string, and you'll get some kind of an error from the compiler because you're trying to add a string and a number. In the second example, here's a declaration of y, and then in the body of the let, we don't see any use of y. And that by itself is not an error. It's perfectly fine to declare a variable that you don't use, although you can imagine generating a warning for that. That doesn't actually cause the program to behave badly. But instead, what we see here is a use of x, and there's no matching definition. So the question is, where is the definition of x? we can't see it, and if there is no outer definition of x, then we'll get an undefined or undeclared variable error here at this point. So these two examples illustrate the idea of scope. The scope of an identifier is that portion of a program in which the identifier is accessible. And just notice that the same identifier may refer to different things in different parts of the program, and different scopes for the same name can't overlap. So whatever the variable x, for example, means, it can only refer to one thing in any given part of the program. And identifiers can have restricted scope. There are lots of examples, and I'm sure you're familiar with them, of identifiers whose scope is less than the entire program. Most programming languages today have what is called static scope, and COOL is an example of a statically scoped language. The characteristic of static scoping is that the scope of a variable depends only on the program text, not on any kind of runtime behavior. So what the program actually does at runtime doesn't matter. The scope is defined purely syntactically from the way you wrote the program. Now, it may come as a surprise that there's any alternative to static scoping. In fact, probably every language that you have used up to now has had static scoping. But there are a few languages that are what are called dynamically scoped. And for a long time, actually, there was an argument about whether static scoping was better than dynamic scoping. Although today, I think it's pretty clear that the static scoping camp has won this discussion. But historically, at least, Lisp was an example of a dynamically scoped language. And it has switched in the meantime. This is actually a long time ago now that it changed to static scoping. Another language, which is now mostly of historical interest, it isn't really used anymore, called Snowball, also had dynamic scoping. And the characteristic of dynamic scoping is that the scope of a variable depends on the execution behavior of the program. So let's take a look at an example of static scoping. So here we have some COOL code and a couple of different declarations of x, and also some different uses of x. Let me erase these underlines so that I can use the color to indicate bindings. So let's take a look at this definition. The question is, which of these uses of x, we have three uses of x here, actually refer to that definition? So it is, in fact, these two. The ones that are outside of the inner let, these actually refer to this definition. So here, if you refer to x, you get the value 0. But this other definition here, the inner definition of x, is used by this use of x. So this use of x gets this meaning of x, which in this case returns the value 1. And what's going on here is that we use the what's called the most closely nested rule. So a variable binds to the definition that is most closely enclosing it of the same name. So this x, the closest enclosing definition of x is this one, but for these two x's, the closest and only enclosing definition of x is this outer one. So in a dynamically scoped language, a variable would refer to the closest binding in the execution of the program, meaning the most recent binding of the variable. So here's an example. Let's say we have a function g, and g defines a variable a, and here it's initialized, say, to 4, and then it calls another function that isn't in the same syntactic scope. So here I've written f right next to g, but actually f could be in some completely other part of the code, and f refers to a. And the question is, what is the value of a here? Well, if we're dynamically scoped, then it's going to be the value that was defined in g, and here f of x will actually return 4. That'll be the result of this call, because this reference to a will refer to this binding or this definition of a in g. And we can't say much more about how dynamic scope works until we talk in a little more detail about how languages are implemented. So we'll talk about dynamic scope again a little bit later on in the course. In COOL, identifier bindings are introduced by a variety of mechanisms. There are class declarations, which introduce class names, method definitions, which introduce method names, and then there are several different ways to introduce object identifiers. And these are the let expressions, formal parameters of functions, attribute definitions in classes, and finally in the branches of case expressions. Now, it's important to understand that not all identifiers follow the most closely nested rule that we outlined before. So, for example, a rather large exception to this rule is class definitions in COOL. So class definitions cannot be nested, and in fact they are globally visible throughout the program. And what does that mean? That means that a class name is defined everywhere. If it's defined anywhere in the program, that class name is available for use anywhere in the program or everywhere in the program. And in particular, a class name can be used before it is defined. So as an example, take a look at this fragment of cool code here. And here we see that in class foo, we declare y to be of type bar, and then later on, we declare class bar. And this is perfectly fine cool code. The fact that bar is used before it is defined has no effect on whether the program is correct. This is a completely legal cool code. Similarly, with attribute names are global within the class in which they are defined. So that means they can be used, again, before they are defined. So for example, I can define a class foo, and I can define a method that uses attribute A, and then later on, only later on, do I define what attribute A is. And that is perfectly legal. So normally, we list attribute definitions before method definitions, but that's not required. Actually, the method and attribute definitions can come in any order we like within a class, and in particular, an attribute can be used before it is defined. Finally, method names have quite complex rules. For example, a method doesn't have to be defined in the class in which it is used. It could just be defined in some parent class. And also, methods can be redefined. So it's possible to do what's called overriding of a method and give a method a new definition, even though it has been defined before. We don't actually have the language yet to talk about these rules with any precision, but we'll be going into this in future videos. In this video, we're going to talk about symbol tables, an important data structure in many compilers. Before we talk about what a symbol table is, I want to talk about a generic algorithm that we're going to be seeing instances of over and over again for the rest of the course. So a lot of semantic analysis, and in fact a lot of code generation, can be expressed as a recursive descent of an abstract syntax tree. And the basic idea is that at each step we do the following three things. We're always processing a particular node in the tree. So if I draw a picture of the abstract syntax tree, we might have a node and some subtrees hanging off of it. And we may do some processing of the node before we do anything else. We arrive at the node, say, from the parent. We come into here from the parent. We do some processing of the node. And I'm just indicating that by coloring it blue to indicate that we did something here. And then we go off and we process the children. Okay? And after we process the children, after we come back to the node, we do something else. We may do some post-processing of the node, and then we return. And of course, at the same time, when we've got off and processed the children, we're processing all their nodes in the same pre and post fashion. So they're getting the same treatment with some stuff being done before each node is touched and some stuff being done after all their children have been processed. Okay? And there are many, many examples of this kind of an algorithm. This is called a recursive descent traversal of a tree. There are some instances in which we'll only process each node before we process the children, some where we only process each node after we process all the children, some where we do both, as illustrated here in this little diagram. And returning to the main topic of this particular video, when we're performing semantic analysis on a portion of the abstract syntax tree, we're going to need to know which identifiers are defined, which identifiers are in scope. An example of this kind of recursive descent strategy is how we can process let bindings to track the set of variables that are in scope. So we have our let node in the abstract syntax tree, and in one subtree we have the initialization, and in the other subtree we have E, the body of the let. All right? And then this is a let for some particular variable, and let's just write that variable inside the parent node here. And so when we begin processing of this node, let's imagine that we're coming from above. So we're doing this, we're processing the abstract syntax tree recursively, and so we reach this point from some parent, and there's going to be a set of symbols that are currently in scope. That's some data structure that lives off to the side. In fact, that's going to be our symbol table. And what is going to happen here? Well, the first thing we're going to have to do is we're going to have to process the initializer. We're going to need to know whether that's whatever function we're doing on this, like type checking or whatever, we might go down and process that first, and we'll pass the symbol table in. Okay, and then we're going to process the body of the let. But when we do that, we're going to pass in the set of symbols that are in scope, but also X is now going to be in scope. So X is going to be added before we process E to the set of symbols. And then when we return from the sub-expression E, it's going to be removed. And so we'll restore the symbol table to its previous state so that after we leave this subtree of the abstract syntax tree, we only have the same set of symbols defined that we had before we entered it. So in the terminology of the three-part algorithm for a recursive descent that we had on the first slide, what are we doing here? Well, before we process E, we're going to add the definition of X to our list of current definitions, overriding any other definition of X that might have been visible outside of the let expression. Then we're going to recurse. We're going to process all of the abstract syntax tree nodes in the body of the let inside of E. And after we finish processing E, we're going to remove the definition of X and restore whatever old definition of X we had. And a symbol table is just a data structure that accomplishes these things. It tracks the current bindings of identifiers at each point in the abstract syntax tree. For a very simple symbol table, we could just use a stack, and it would have just, say, the following three operations. We can add a symbol to the symbol table, and that will just push the symbol, push the variable onto the stack and whatever other information we want, like its type. We'll have a find symbol operation that will look up the current definition for a symbol, and that can be done simply by searching the stack, starting from the top, for the first occurrence of the variable name. And this will automatically take care of the hiding of old definitions. So for example, if we have a stack that, say, has X, Y, and Z on it, and then we come into a scope that introduces a new Y, we would push Y on top, and now if we search through the stack, we would find this Y first, that effectively hiding the old definition of Y. And then when we leave a scope, we can remove a symbol simply by popping the stack. We'll just pop the current variable off of the stack. That will get rid of the most recent definition, and leave the stack, leave the set of definitions in the same state it was before we entered the node at all. So in this example, if we left the scope where the outer Y was defined and that was popped off the stack, so that was gone, now when we search for Y, we'll find the outer definition, the one that was defined outside of that inner scope. So this simple symbol table works well for let because the symbols are added one at a time and because declarations are perfectly nested. And in fact, the fact that declarations are perfectly nested is really the whole reason that we can use a stack. So take a look at this little example. Let's say we have three nested lets, and here I'm not showing the initializers in the left subtrees. They don't matter for what I want to illustrate. So if you think about it, as we walk from the root here down to the inner bindings, and we're pushing things on the stack, we'll push things on the stack in the order X, Y, and then Z. And then as we leave, after we've processed this subtree, and we're leaving it, walking back out, we're going to encounter these let scopes in exactly the reverse order, and popping them off the stack is exactly the order in which we want to remove them, and that's why a stack works well. So this structure works fine for lets, but for some other constructs it's not quite as good as it could be. So for example, consider the following piece of code. Illegal piece of code, I should add. Let's say we're declaring a method and it has two arguments named X. Now that's not legal, but in order to detect that it's not legal, why is it not legal? It's not legal because they're both defined in the same scope. So functions or methods have the property that they introduce multiple names at once into the same scope, and it's not quite so easy to use a stack where we only add one thing at a time or one name at a time to model simultaneous definition in a scope. So this problem is easily solved with just a slightly fancier symbol table. Here is the revised interface now with 5 methods instead of 3. The biggest change is that we now have explicit enter and exit scope functions. And so these functions start a new nested scope and exit a current scope. And the way to think about this is that our new structure is a stack of scopes. So what is on the stack is an entire scope, and then in a scope are all the variables that are defined at the same level within that single scope. So just like before, we have a find symbol operation that will look up a variable name, and it will return the current definition or null if there is no definition in any scope that's currently available. We'll have an add symbol operation that adds a new symbol to the table, and it adds it in the current scope, so whatever scope is at the top of our scope stack. And then one more new operation, check scope, will return true if X is already defined in the current scope. So this, just to be clear on what this does, this returns true if X is defined in exactly the top scope. It doesn't return true unless X is defined in the scope at the very, very top of the stack, and this allows you to check for double definition. So for example, in the code that I had before on the previous slide, if we had two declarations of X, how would we check this? Well, we would add X to the symbol table in the current scope, and then we would ask, well, is X already defined in this scope for the second one? And this interface would return true, and we would know to raise an error saying that X had been multiply defined. Finally, let me just add that this is the symbol table interface, or something very close to this is the symbol table interface that is supplied with the Cool project, and there's already an implementation of this interface provided if you don't want to write your own. So let's wrap up this video by talking a little bit about class names, which behave quite differently from the variables introduced in let bindings and in function parameters. In particular, class names can be used before they are defined, as we discussed a few videos ago. And what that means is that we can't check class names in a single pass. We can't just walk over the program once and check whether every class that is used is defined, because we don't know that we've seen all the definitions of the classes until we reach the very end of the program. And so there is a solution to this. We have to make two passes over the program. In the first pass, we gather all the class definitions. We go through and we find every place where a class is defined. We record all of those names. And then in the second pass, we go through and look at the bodies of the classes and make sure they only use classes that were defined. And the lesson here, this is actually not complicated to implement. I think it's quite clear, or should be quite clear, how this will work. But the message here is that semantic analysis is going to require multiple passes, and probably more than two. And in fact, you should not be afraid when structuring your compiler to add lots and lots of simple passes if that makes your life easier. So it's better to break something up into, say, 3 or 4 simple passes rather than to have one very, very complicated pass where all the code is entangled. I think you'll find it much easier to debug your compilers if you're willing to make multiple passes over the input. Welcome back. In this video, we're going to have an introduction to types. So a very basic question to ask is, what is a type anyway? And this question is worth asking because the notion of type, what a type is, does vary from programming language to programming language. Now, roughly speaking, the consensus is that a type is a set of values and also, perhaps more importantly, a set of operations that are unique to those values, a set of operations that are defined on those values. So for example, if I look at the type of integers, there are some operations that you can do on integers. You can do things like you can add and you can subtract integers, and you can compare integers, whether they're greater than or equal or less than. Okay, and then these operations are, you know about numbers. And then there are operations on strings. And strings are a different type. They have operations like concatenation and testing whether a string is an empty string or not. And there's a variety of other functions that are defined on strings. And the important thing is that these operations are different from the operations defined on integers, and we don't want to mix them up. It would be bad if we started doing string operations on integers, for example. We would just get nonsense. So in modern programming languages, types are expressed in a number of different ways. In object-oriented languages, often we see classes being the notion of type. So particularly in Cool, the class names are the types. They're all, with one exception, called self-type, the class names are exactly the types. And I just want to point out that this need not be the case. It happens that it's often convenient in object-oriented languages to equate classes and types, but there are other designs where the classes are not the only kinds of types, or whether they're And in some languages where there's no notion of class, the types are completely different things. So classes and types are really two different things that happen to be identified in a lot of object-oriented language designs, and I just want you to be aware that that's not necessarily the only way to do it. So consider the assembly language fragment, add R1, R2, R3. And what does this actually do? Well, it takes the contents of register R2 and the contents of register R3, it adds them together, and it puts the result in register R1. And the question is, what are the types of R1, R2, and R3? And you might hope that they're integers, but in fact, this is a trick question because at the assembly language level, I can't tell. There's nothing that prevents R1, R2, and R3 from having arbitrary types. They could be representatives of any kind of type, and because they're just a bunch of registers with zeros and ones in them, the add operation will be happy to take them and add them up, even if it doesn't make sense, and produce a bit pattern that it stores into R1. So to make this a little clearer, perhaps, it's useful to think about certain operations that are legal for values of each type. So for example, it would make perfect sense to add two integers. If I have two bit patterns that represent integers, then when I sum them up, I will get a bit pattern that represents the sum of those two integers. But on the other hand, if I take a function pointer and an integer and I add them together, I really don't get anything. I mean, this is the function pointer is a bit pattern, the integer is a bit pattern. I can take those two bit patterns, I can run them through and add, and I do get out a new set of bits, but there is no useful interpretation of that result. The resulting thing I get doesn't mean anything. But the problem is that both of these have the same assembly language implementation. Okay, nothing at the assembly language level, these two operations look exactly the same. So I can't tell at the assembly language level which one of these I'm doing. And if I want there to be types, if I want to make sure that I only do operations on the correct, that I only do certain operations on their correct types, then I need some kind of type description and some sort of type system to enforce those distinctions. So perhaps I'm belaboring this point, but I think it's important. So one more time. A language's type system specifies which operations are valid for which types. And then the goal of type checking is to ensure that operations are used only with the correct types. And by doing this, type checking enforces the intended interpretation of values because nothing else is going to check. Once we get down to the machine code level, it's all just a lot of zeros and ones, and the machine will be happy to do whatever operations we tell it to on those zeros and ones, whether or not those operations make sense. So the purpose of type systems is to enforce the intended interpretations of those bit patterns and make sure that if I have a bit pattern for integers that I don't do any non-integer operation on that and get something that is meaningless. Today, programming languages fall into three different categories with respect to how they treat types. There are the statically typed languages, where all or almost all the checking of types is done as part of compilation. And Cool is one of these, and other languages that you've probably seen, like C and Java, are also statically typed. Then there are the dynamically typed languages, where almost all of the checking of types is done as part of program execution. And the Lisp family of languages, like Scheme and Lisp itself, are in this category, as are languages like Python and Perl. Right? And so you probably used or heard of, at least, some of those languages. And then finally, there are the untyped languages where no type checking is done at all, either at compile time or at runtime. And this is basically what machine code does. So machine code has no notion of types and enforces no abstraction boundaries when it executes. For decades, there has been a debate about the relative merits of static versus dynamic typing. And without taking sides, let me lay out for you what the various proponents on each side say. So the people who believe in static typing say that static checking catches many programming errors at compile time, and it also avoids the overhead of runtime type checks. If I've done all the type checking at compile time, well, I don't have to check the types at runtime. I don't have to check when I go to do an operation that the arguments are of the correct type because I already did that check once and for all at compile time. And these things are both definitely true. These are the two big advantages of static checking. First of all, it proves that some errors can never happen. Those are caught at compile time, and so I never have to worry about those errors at runtime. And also, it's faster. Dynamic typing proponents counter that static type systems are restrictive. So essentially a static type system has to prove that the program is well typed, that all the types make sense, and it does this by restricting what kinds of programs you can write. There are some programs that are more difficult to write in a statically typed language because the compiler has a hard time proving them correct. And there's also a belief that I see commonly stated that rapid prototyping is more difficult with a static type system. And I think the idea here is that if you're prototyping something, if you're exploring some idea, you may not actually know exactly what all the types are at that point in time, and having to commit to something that's going to work in all cases, to having a type correct program when you're just trying to fiddle around and figure out what it is you're trying to do, that's very constraining and makes the work go quite a bit slower. So what's the actual situation in practice today? Well, an awful lot of code is written in statically typed languages, and the practical statically typed languages that people use a lot always have some kind of escape mechanism. So in C and Java and C++, you have some notion of unsafe cast. In C, an unsafe cast can just result in a runtime crash. In Java, it results in an uncaught exception at runtime when you have an unsafe or a failed downcast. But the effect is that you can get runtime errors for type reasons. Now, on the dynamic typing side, the people who program in dynamic languages, they always end up, or seem to end up, retrofitting static typing to these dynamically typed languages. So typically, if a dynamically typed language becomes popular enough, then people start trying to write optimizing compilers for them, and the first thing that people want to have in an optimizing compiler is some type information, because it helps to generate much better code. And so people wind up going back and trying to figure out how to get as many types as they can from these dynamically typed languages as soon as they start trying to build serious tools to improve the programs written in these languages. And in my opinion, it's really debatable whether either compromise, because both of these are compromises on the either strict static or strict dynamic point of view, whether either one of these represents the best or the worst of both worlds. But this is certainly where we are today in practice. Now, Cool is a statically typed language, and the types that are available in Cool are the class names. So every time you define a class, you define a new type, and the special reserved symbol self-type, which we'll be talking about in a separate video all of its own. And the way Cool works is that the user declares the types for identifiers. So for every identifier, you have to say what its type is. But then the compiler does the rest of the work. The compiler infers the type for expressions. And in particular, the compiler assigns a type to every single expression in the program. So it will go through the entire abstract syntax tree, and using the declared types for identifiers, it will calculate a type for every expression and sub-expression. To wrap up, it's worth mentioning that there's a couple of different terms that people use for the process of computing types, and that they mean slightly different things. So the simpler problem is what is known as type checking. Here we have a fully typed program, meaning we have an abstract syntax tree with all the types filled in on every node, and our only job is to check that the types are correct. So we can just look at each node and its neighbors and confirm that the types are correct in that part of the tree, and we can do this for every part of the tree and check that the program is typed correct. Type inference, on the other hand, is the process of filling in missing type information. So here the view is that we have an abstract syntax tree with no types on it, or perhaps just a few types in key locations on it, say on the declared variables, and then we want to fill in missing types. We have some nodes in there with absolutely no type information at all, and it's not just a question of confirming or checking that the types are correct. We actually have to fill in the missing type information. And these two things are different. Actually, they're actually in many languages they're actually very, very different. But people often use the terms interchangeably, and I will not be particularly careful in my videos about which term I'm using either. In this video, we're going to talk about type checking in Cool. Thus far, we've seen two examples of formal notation used to specify parts of a compiler. Regular expressions were used in lexical analysis and context-free grammars, which we used in parsing. It turns out that there's another formalism which has gained widespread acceptance in type checking, and that's logical rules of inference. Inference rules are logical statements that have the form, if some hypothesis is true, then some conclusion is true. So inference rules are implication statements that some hypothesis implies some conclusion. And in the particular case of type checking, an example or a typical kind of reasoning that we see in type checking is that if a couple of expressions have certain types, then some other expression is guaranteed to have a certain type. And so clearly the type checking statement here is an example of an inference rule. And inference rule notation is just a compact way of encoding these kinds of if-then statements. Now, if you haven't seen this notation before, it will be unfamiliar, but actually it's quite easy to read with practice. And we'll start with a very simple system and gradually add features. So we'll use logical conjunction for the English word and implication for the combination of English words if and then. And now one special thing, the string x:t is read that x has type t. So this is a logical assertion saying that x has a particular type. So now consider the following very simple type rule. If E1 has type int and E2 has type int, then E1 plus E2 also has type int. And we can just take the definitions we gave on the previous slide and gradually reduce this to a mathematical statement. So for example, we can replace the if-then with an implication, and we can replace the word and with a conjunction, and now we just have these has type statements. All right, and we had a notation for that, and we wind up with this purely mathematical statement which says exactly the same thing, that if E1 has type int and E2 has type int, that implies that E1 plus E2 has type int. Now notice that that statement that we just wrote out is a special case of an inference rule. It's a bunch of hypotheses conjoined together that implies some conclusion. The traditional notation for inference rules is given here. The hypotheses are written above a horizontal line, and the conclusion is written below. And it means exactly the same thing as what we had on the previous slide, namely that if all the things above the horizontal line are true, these are all the hypotheses, then the thing below the horizontal line can be concluded to be true. And there's one piece of new notation here. This is the turnstiles that are used for the hypotheses and the conclusion. And the turnstile is read, "It is provable that." And what this means is that we're just going to say explicitly that something is provable in the system of rules that we are defining. And so the way you would read this is that if it is provable that all of these hypotheses are true, so if it's provable that the first hypothesis is true, all the middle hypotheses, and if it is provable that the last hypothesis is true, then it is provable that the conclusion is true. And cool type rules are going to have the following kinds of hypotheses and conclusions. We're going to prove within the system that some expression has a particular type. So with those definitions out of the way, we actually have enough to write at least a few simple type rules. So if I is an integer literal, if it's an integer constant appearing in my program, then this rule says it is provable that I has type int. So every integer constant has type int. And here's the rule for add, written out now in the inference rule notation. If it is provable that E1 has type int and is provable that E2 has type int, then it is provable that E1 plus E2 has type int. So notice that these rules give templates for describing how to type integers and expressions. The rule for integer constants just used a generic integer I. It didn't give a separate rule for every possible integer. And the rule for plus used expressions E1 and E2. It didn't tell you what particular expressions they were. It just said, give me any expression E1, any expressions E1 and E2 that have type int. And so we can plug any expressions we want in that satisfy the hypotheses, and then we can produce a complete typing for actual expressions. So as a concrete example, let's show that 1 plus 2 has type int. So we want to type the expression 1 plus 2, and since we know the rule for add, that means we need to construct a proof of the type of the number 1 and a proof of the type of the number 2. And we have a rule for dealing with integer constants, namely we can prove because 1 is an integer constant that it has type int, and we can prove that 2 is type int, and then now we have the two hypotheses we need for the sum expression, and we can prove that 1 plus 2 has type int. So an important property of any reasonable type system is that it be sound. And soundness here is a correctness condition. what we want is that whenever the type system can prove that some expression has a particular type t, then if I actually run that program, if I take E and I execute it on a computer, the value that it returns, the value that comes back after running E, in fact has the type predicted by the type system. So if the type system is able to give types to things that actually reflects what kind of value you get when you run the program, then we say that the type system is sound. Now clearly we only want sound rules, but some sound rules are actually quite a bit better than others. So for example, if I have an integer literal and I want to give it a type, well, I showed you the best possible rule before where we said that I has type int, but it would also be correct, just not very precise, to say that I has type object. Certainly if I evaluate an integer, I will get back an object because every integer in cool is also an object, but this isn't all that useful because now I can't do any of the integer operations. And so there are lots of different sound rules. There's not just one unique rule for any given cool expression that will be sound, but some of them are better than others. And in the case of integer literals, the one we really want is that integer literal has type int because that's the most specific type that we can give to that kind of program. To summarize, type checking proves facts of the form E has type t. And notice that this proof is on the structure of the abstract syntax tree. So for the expression 1 plus 2, we prove something about 1 plus 2, but by first proving something about each of the sub-expressions. So we proved that the sub-expressions had type int, and then we managed to prove that the whole thing had type int. Okay? And so the proof has the same shape as the abstract syntax tree. You can look at this proof as a tree. Now the root of the tree in the case of the proof is at the bottom. Usually we draw the abstract syntax tree with the root at the top. So this tree looks like this, whereas we often draw the abstract syntax tree in the other way around. But the important thing here is that the proof has the shape of the abstract syntax tree, and there's one type rule that's used for each abstract syntax tree node. So there's a very direct correspondence between the structure of the proof and the shape of the abstract syntax tree. And in general, the type rule used for a particular node of the abstract syntax tree, the hypotheses, are going to be the proofs of the types of E's sub-expressions. So whatever expressions make up E, we're going to need types for them first, and the conclusion at that particular node will be the type of the entire expression E. And in this way, you can see that types are computed in a bottom-up pass over the abstract syntax tree. That is, I assign first types to the leaves, like here I know that 1 has type int and 2 has type int, and then the types flow towards the root. I'm able to compute then the next level of the abstract syntax tree and so on. And once I've computed the types of all the sub-expressions of a node, then I can compute the type at that node. In this video, we're going to continue our development of cool type checking with a discussion of type environments. Let's begin by doing some more type rules. So here's one for the constant false. So it's provable that the constant false has the type bool, and that's not too surprising. If I have a string literal, s, then it's provable that that has type string, and that's also not very surprising. The expression new t produces an object of type t, and the type rule for that is very straightforward. New t has type t. And we're just going to ignore self-type for now. As I mentioned in an earlier video, we'll deal with self-type later in a video all its own. Here are a couple of more rules. If it's provable that an expression E has type bool, then the Boolean complement of E, not E, also has type bool. And finally, perhaps our most complex rule so far, the rule for a while loop. And recall that the E1 here is the predicate of the loop. This is what determines if we keep executing the loop or not. And E2 is the body of the loop. And so E1 is required to have type bool. It needs to be provable that E1 has type bool. And we allow E2, the body of the loop, to have an arbitrary type. It can have any type T. It has to have some type, so it has to be typable under some rules. But we don't care what the type is, because the type of the entire expression is just object. We don't actually return, this expression doesn't return an interesting value, doesn't produce an interesting value, and to discourage people from trying to rely on it, we just type the whole thing as object. And this is a little bit of a design decision. Now we could have designed a language, for example, where the type of a while loop was type T, and that you would get the last value of the loop that was executed. But the problem is that if E1, the predicate of the loop, is false on entry to the loop the first time, then you never evaluate E2 and no value is produced. And in that case, you would get a void value, which if somebody tried to dereference it, would result in a runtime error. And so to discourage programmers from relying on the loop producing a meaningful value, we could just type it as object. So far, it's been pretty straightforward to define reasonable type rules for every construct that we've looked at. But now we actually come to a problem. Let's say we have an expression which consists just of a single variable name, and that's a perfectly valid, cool expression. And the question is, what is the type of that variable? Call it x. And as you can see, when we're just looking at x by itself, we don't have enough information to give x a type. This local structural rule does not carry any information about the type of x. And stepping back one level, inference rules have the property that all the information needs to be local. Everything we need to know to carry out the function of the rule has to be present in the rule itself. There are no external data structures. There's nothing we're passing around here that's on the side. Everything has to be encoded in this rule, and so far at least, we just don't know enough to say what the type of a variable should be. So the solution to this problem is just to put more information in the rules, and that's what we're going to do. So a type environment gives types for free variables. So what is a free variable? A variable is free in an expression if it is not defined within that expression. So for example, in the expression x, x is free. In the expression x plus y, well, here this expression uses both x and y, and there's no definition of either x or y in that expression, so x and y are free in that expression. If I have let y dot dot dot, so I'm declaring a variable y in x plus y, well, what's free in this expression? Well, this expression uses x and y, but the use of y is governed by a definition of y that occurs within the expression itself. So we say here that y is bound. Y is a bound variable in this expression, but x is still free. So only x is free in that expression. And the idea here is that if I have an expression with free variables and you want me to type check it, you have to tell me what the types of those variables are. So I can type check x if you tell me what the type of x is. I can type check x plus y if you tell me the types of x and y. And I can type check this expression, this let expression, if you tell me the type of its one free variable x. The type of y will be given by the declaration in the let, but you still have to tell me what the type of x is. And so the free variables are just those variables where you have to give me the information, and then I can carry out the type checking. And a type environment encodes this information. So a type environment is a function from object identifiers, from variable names, to types. So let O be a type environment, one of these functions from object identifier names to types. And now we're going to extend the kinds of logical statements that we prove to look like this. And the way this is going to be read is that under the assumptions that variables have the types given by O, so the assumptions go over here on the left side of the turnstile. These are the assumptions that we're making about the free variables in E. So the assumption that, free variables have the types given by O, it is provable, that's this turnstile here, that the expression E has type T. And so this notation very nicely separates what we're assuming, this is input to our process of figuring out what the type is, from what we're proving. So if you tell me the types of the free variables as given by O, then I can tell you the type of E. The type environment has to be added to all the rules that we've gone through so far. So for example, for integer literals, if I have some set of assumptions about the types of variables, that doesn't really change, in fact it doesn't change what the type is of an integer literal. Any integer literal will still have type int. And so in this case, for this particular kind of expression, I, we don't use any of our assumptions about the types of variables. Now, it's a little bit different with the case of a sum expression. So if I have the expression e1 plus e2, and I have some assumptions, O, about the types of variables, well, then I want to prove that E1 has type int, and I'm going to do that using the types of the variables given by O. So E1 might contain free variables, and I'll need to look in O to figure out what the types of those variables are. And similarly for E2, I will type E2 under the same set of assumptions. And if E1 has type int under the assumptions O and E2 has type int under the assumptions O, well, then I can conclude that E1 plus E2 has type int under the same set of assumptions O. And we can also write new rules. So now our big problem with free variables becomes a very easy problem. If I want to know what the type of x is, and there's a missing O here, if I want to know what the type of x is, I simply look it up in my object environment. So under the assumption that the variables have the types given by O, what is the type of x? Well, I'll look up in O what the type of x is assumed to be, and then I can prove that x has that type t. So now let's take a look at a rule that actually does something interesting with the variables from the point of view of the environments. So here is a let expression, and let's remind ourselves what this does. This is a let expression that has no initialization. So it says that x is going to be a new variable. It's going to have type t0, and that variable is going to be visible in the sub-expression E1. And so now how am I going to type check that? Well, I'm going to type check E1 in some kind of environment, and this is new notation here, so let me define what it means. So remember, O is a function. It maps variable names to types, and O t/x, this notation here, is also a function. And what this is the function O modified at the single point x to return t. So in particular, this function, this whole thing here is one function. This whole thing I'm underlining here is a function. That applied to x returns t. So that says that this set of assumptions says that x has type t, and for any other variable, if I apply it to some other variable y, where x is different from y, well, then I just get whatever type y has in O. Okay? So what this rule then says is I'm going to type check E1 in the same environment O, except that at point x, it's going to have the type t0. So I'm going to change just the type of x to have type t0 because that's the type of the new identifier that's bound in E1. And all the other types will be the same. And using those assumptions, I'll try to prove that E1 has some type. I will get a type for E1, and then that will be the type of the entire let expression. Now, notice something about the type environment. What this says is that before we type check E1, we need to modify our set of assumptions, modify our type environment to include a new assumption about x. Then we type check E1, and then, of course, when we leave type checking E1, we're going to remove that assumption about x, that new assumption, because outside of the let, we just have the original set of assumptions O. And so I hope that that terminology and that description reminds you of something we talked about earlier, because this type environment is really implemented by the symbol table. So in our rules, the type environment carries around the information that will be stored or is typically stored in the symbol table of a compiler. To summarize this video, the type environment gives types to the free identifiers in the current scope. And this is very important because it doesn't even really make sense to talk about type checking an expression unless we have some information for the types of the free identifiers. And the type environment is just a way of formalizing that, of giving a name to some set of assumptions about what the types of those free identifiers are. Notice that the type environment is passed down the abstract syntax tree from the root towards the leaves. That is, as we pass through definitions, the type environment is extended with new definitions, for example, in let expressions. And so the type environment will grow as you pass from the root of the abstract syntax tree down towards the leaves of the abstract syntax tree. And then the types are computed up the abstract syntax tree from the leaves towards the root. So we begin at the leaves, get all the types of the leaf expressions, most of which are very easy. Things like integers and string constants have the obvious types, and we just look up the types of variables in the type environment. And then we compute the types for the more complicated expressions in a bottom-up fashion. In this video, we're going to talk about subtyping, another important idea in COOL and other object-oriented languages. Let's begin by taking a look at the typing rule for let with initialization. So last time we looked at the let rule but didn't have the initializer, and so let's just see how adding the initializer right here changes things. So what's going to happen here? Well, first of all, notice that the body of the rule is almost the same. So we type check E1 in an environment where X has type T0, the type it's declared to have in the let, and all the other variables have whatever types O gives them, and we get out some type T1, and that will be the type of the whole thing. So this piece right here is exactly the same as before. So what's new is this line where we type check the initializer. And so how does that work? Well, first of all, under the assumptions O, we type check E0 and we get some type T0. And now this is really an aside from the main point, but notice that we use the environment O. In particular, X, the new definition of X is not available in E0. So if E0 uses the name X, that means it uses the name of some other X that's defined outside of the let, because we didn't include this definition of X in the environment for type checking E0. All right, now, but the main point, the thing I want to point out on this slide, is that E0 here has type T0, which is exactly the same type as X. And that's a requirement of this rule. It says that E0 has to have the same type as X. And that's actually fairly weak, because there's really no problem if E0 has a type which is a subtype of T0. T0 can hold any subtype of T0, and that would be absolutely fine. But here we've limited ourselves to only allowing initializers that exactly match the type of X. So we can do better if we introduce the subtyping relation on classes. And the most obvious form of subtyping is that if X is a class and it inherits directly from Y, meaning there's a line in the code that says X inherits from Y, then X should be a subtype of Y. And furthermore, this relationship is transitive. So if X is a subtype of Y and Y is a subtype of Z, then X is a subtype of Z. And finally, as you might expect, it's also reflexive. So every class is a subtype of itself. And using subtyping, we can write out a better version of the let rule with initialization. So once again, the body, the part of the rule that deals with the body of the let is exactly the same as before. So let's not look at that. And now what we're going to do is we're going to type check E0 and we get some type T0 out. And then T0 now is only required to be a subtype of T. So this line here is another hypothesis, and it just says that T0 has to be a subtype of T. And what is T? Well, T is now the type that X is declared to be. So this allows E0 to have a type that's different from the type of X. And the only issue here is that more programs will type check with this rule than the previous one. The previous rule we had was certainly correct. Any program that compiled with that rule would run correctly. But this is a more permissive and still correct rule. More programs will compile and type check correctly using this rule. Subtyping shows up in a number of places in the COOL type system. Here's the rule for assignment, which is in many ways similar to the rule for let. So how does an assignment work? Well, on the left-hand side is a variable. On the right-hand side is an expression. We're going to evaluate the expression and assign whatever value we get back to the variable on the left-hand side. And so how is this type checked? Well, first of all, we have to look up the type of X in the environment, and we discover it has some type T0. And then we type check E1 in the same environment, so the set of variables here is not changing. And so we type check E1 environment O, and we get some type T1. And now what has to be true for this assignment to be correct? Well, it has to be possible for X to hold a value of type T1. So X's type T0 has to be a supertype, has to be bigger than the type of T1. So if this constraint is satisfied, then the assignment is correct. Another example that uses subtyping is the rule for attribute initialization, which except for the scope of identifiers is very, very similar to the rule for normal assignment. So recall what a class looks like. You can declare a class in COOL, and it has at the top level some set of attributes and methods. And what does an attribute definition look like? Well, it looks like one of these things. It's a variable declared to have some type, and it can have an initializer on the right-hand side. And so in what environment then is this initializer type checked? Well, it's type checked in this special environment O sub c, which just consists of the types of all the attributes that are declared in class C. So this means we have to make a pass over the class definition, pull out all the attribute definitions, all the names of the variables and their types, build an environment that records all that information, and then we can type check the initializers, because remember, the initializer for an attribute can refer to any of the attributes of the class. So let's take a look at how this works. First, we look up the type of x in the environment, that's some type t0. Now we type check e1 in the same environment, that's some type t1. And then just as with assignment, t1 needs to be a subset or a subtype of the type t0. Now we come to another interesting example, how we type check an if-then-else. And the important thing about if-then-else is that when we're doing type checking, we don't know which branch is going to be taken. We don't know whether the program is going to execute E1 or E2. And in general, actually, this if statement may, or this if expression may execute multiple times during a run of the program, and sometimes it may execute E1, and other times it may execute E2. And so what that means is that the resulting type of an if-then-else is either the type of E1 or the type of E2, and we don't know at compile time which one it's going to be. So the best we can do is to say the type of the entire if-then-else is the smallest supertype larger than the type of either E1 or E2. The need to compute an upper bound over two or more types comes up often enough that we're going to give the operation a special name. We'll call it the lub, or least upper bound, of x and y. And the least upper bound of x and y is going to be z if z is an upper bound, so meaning it's bigger than both x and y. And also if it is the least among all possible upper bounds. So what this line here says is that there is some other z prime that's bigger than x and y, well then z has to be smaller than z prime. So z is the least, it is the smallest of all the possible upper bounds of x and y. And in COOL and in most object-oriented languages, the least upper bound of two types is just their least common ancestor in the inheritance tree. So typically, the inheritance tree is rooted at object or some similarly named class that includes all the possible classes of the program, and then there's some kind of a hierarchy, which is a tree that descends from object. And if I want to find the least upper bound of two types, say this type and this type, I just have to walk back through the tree until I find their least common ancestor. And so in this case, if I pick these two types out of my tree, this would be the least upper bound of those two types. Now we can give a type checking rule for if-then-else. So the first thing to notice about if-then-else expressions is that they do not affect the environment. And if-then-else neither introduces nor removes any variables from the environment, so all the sub-expressions are typed in the same environment as the entire expression. Now the predicate of the if-then-else E0, well, that should have type bool, because that's our decision whether we're going to take the true branch or the false branch. But then the two branches can have different types. E1 just has to have some type T1, and E2 just has to have some type T2. So notice again what this is saying. This is just saying that E1 and E2 do have to type check. They have to be type correct, but we don't care what the type is. The type can be anything. And then the type of the entire expression is just going to be the least upper bound of T1 and T2, because that's going to be the best estimate we can give to the final type of the expression, given that the true branch might return T1, something of type T1, and the false branch might return something of type T2. The rule for case expressions is the most complex one we've seen so far, but really it's just a glorified if-then-else, and it's relatively easy to understand if we just pull it apart. So let's begin by reminding ourselves of what case does. First of all, it looks at E0, it evaluates E0, and then it looks at the runtime type of E0. So it takes the dynamic class of E0, and then it looks at the first branch. And what is it going to do? It's going to compare the type of E0 at runtime to the type T1. And if T1 is a supertype of the runtime type of E0, and in fact it is the smallest of all the possible branches, it's the smallest supertype of all the possible branches, then it's going to pick this branch. It's going to bind x1 to the value. It's going to give it the type T1, so it's going to bind x1 to the value of E0. It's going to retype it as type T1, and that's going to evaluate E1. So you can see in what sense it's a glorified if-then-else. We're just picking the best matching branch, the one whose declared type, most closely matches the runtime type of E0, and then we're going to execute that branch with the variable that's named in that branch bound to the type of E0. So let's see how the typing works out. So first we type check E0 and we get some type T0. And now what's going to happen? Well, if we select the first branch, well, then we're going to take the environment and we're going to extend it with the new variable x1, which is going to have type T1. And so we only take this branch, remember, if the runtime type of E0 matches T1 most closely among all the branches. But if we do take it, then we're going to execute E1 in this environment, and we'll get back something of some type T1 prime. And similarly for all the other branches, until finally the last branch, which is exactly the same as the first one, just with the letter N replacing the number 1. And so since we don't know which branch is going to match at runtime, it could be any of the branches that actually executes, and therefore the type of the entire expression is just going to be the least upper bound over all of the types of the various branches. And here I've just extended least upper bound from a binary operation to an n-ary operation. That should be clear enough. We're just going to take the least upper bound over all of these types. In this video, we're going to continue our discussion of type checking in COOL with the rules for type checking methods and method calls. So here's the situation when we want to type check a method call. Let's say that we have a dispatch on some expression E0 and we're calling some method named f, and we have some arguments E1 through En. Well, so clearly we're going to type check E0 and it's going to have some type T0, and similarly we're going to type check all of the arguments and they're going to have some types. And then the question is, what is the return type of this method call? What kind of value do we get back after we call this method? And as you can probably see, we're in a very similar situation here that we were in before when we were trying to type check a variable reference. We have this name f, and we don't know anything about what it does. We don't know what the behavior of f is, and unless we have some information about f's behavior, we can't really say what kind of value it is going to return. An added wrinkle in COOL is that method and object identifiers live in different namespaces. That is, it's possible in the same scope to have a method called foo and also an object called foo, and we won't get the two confused. They are different enough and used differently enough in the language that we can always tell when we're talking about the object foo and when we're talking about the method foo. But what this means, in effect, is that there's two different environments in COOL, one for objects and one for methods. And so in the type rules, this is going to be reflected by having a separate mapping, a separate method environment that's going to record the signature of each of the methods. And a signature, this is a standard name that you'll probably hear used in other contexts, but the signature of a function is just its input and output types. And so this table, M, is going to take the name of a class, it's going to take the name of a method in that class, and it's just going to tell us what are the argument types of the method. So all but the last type in the list here is one of the argument types of the method, and then the last type is the result type. That's the type of the return value. So the way we're going to write the method signature is just as a tuple or a list of types. The first, all but the last one taken together are the types of the arguments in order, and then the very last one is a type of the result. And so an entry like this in our method environment just means that f has a signature that looks like this. It takes n arguments with the respective types and it returns something of type tn plus 1. So with the method environment added to our rules, now we can write a rule for dispatch. So notice, first of all, that we have these two mappings, one for object identifiers and one for method names on the left-hand side of the turnstile. We have to propagate that method environment through all of the typings for the sub-expressions. And for the case of method dispatch, we just type the type of the expression that we're dispatching to, E0, and all of the arguments, and get types T1 through Tn. And then we look up the type of f in the class T0. So what class are we dispatching to? Well, that's going to be to the class of E0. And so where do we look up M in our environment? Well, there better be a method called F defined in class T0, and it must have some signature with the right number of arguments. And then the actual arguments that we're passing, the E1 through En, their types have to be subtypes of the declared formal parameters. So here, the signature of F says that, for example, the first argument of F has type T1 prime, and so we're going to require that the type of E1 be some type T1 such that T1 is a subtype of T1 prime, and similarly for all the other arguments of the method call. And if all of that checks out, if F has a signature like this and all these subtype requirements on the actual arguments and the formal arguments match, then we're going to say that the entire expression, this dispatch, returns something of type Tn+1, the return type of the method. The typing rule for static dispatch is very similar to the rule for regular dispatch. So recall that syntactically, the only thing that's different is that the programmer writes the name of the class at which they wish to run the method. So instead of running the method F as defined in the class E0, whatever that class happens to be, we're going to run whatever the method F happens to be in some ancestor class of the class of E0. And how is that expressed in the type rules? Well, once again, we type E0 and all of the arguments. And now we require that whatever the type was we discovered for E0, it has to be a subtype of T. So T has to be an ancestor type in the class hierarchy of the type of E0. And moreover, that class T had better have a method called F that has the right number of arguments with the right kind of type such that all the type constraints work out, that the actual argument types are subtypes of the corresponding formal argument types. And then if all of that is true, we'll be able to conclude that the entire dispatch expression has a type Tn+1, which is the return type of the method. The method environment has to be added to all the other type rules in our system. This is really easy to do because only the dispatch rules actually care about what the methods are. All the rest of the rules just pass the method environment along. So what do I mean by that? Well, here's our rule for add with just the object environment. So now what we're going to do is we're going to add a method environment, and the sub-expressions will be just type checked in exactly the same method environment as the entire expression. And all the other rules simply pass down the method environment from the root towards the leaves without changing it, just as in this rule. Now, it turns out that for some cases involving self-type, we actually need one more thing in our environment. And so the actual full environment for cool type checking consists of three things. First of all, there's the mapping O that gives types to object IDs. There's this mapping M that gives types to methods. And finally, we just need to know the name of the current class. So whatever class the expression we're type checking actually sits in. So the full form of a sentence in the cool type checking logic looks like this. And it's read as follows: under the assumption that the object identifiers have the types given by O, that the methods have the signatures given by M, and that the expression sits in the class C, then we can prove that the expression E has the type T. And here's an example, the add example, the rule for addition again, written out with the full environment. So the rules that I've given you for type checking here are cool specific, and some other languages have very different rules. But there are some general themes of type checking. First of all, type rules are defined on the structure of expressions. So they're typically done in this inductive fashion, where the type of an expression depends on the types of its sub-expressions. And also the types of variables and more generally any free names in an expression, things like method names, they're going to be modeled by an environment. So we're going to have some mapping sitting around that tells us for any kind of free name in an expression what assumptions the type rules should make about the types of those names. And one thing you've probably noticed by now, but it's worth saying explicitly, is that type rules are really very compact. The notation is not complicated, but there's actually a lot of information in these rules, and you have to take some time to sit and read them carefully to really understand what they are saying. In this video, we're going to talk about how one takes the type checking rules and translates them into an implementation. The high-level overview of cool type checking is that it can be implemented in a single traversal over the abstract syntax tree. And there's actually two phases here. There's the top-down phase, in which the type environment is passed down the tree. And then there's a bottom-up phase, in which the types are passed back up. So we start at the root of the tree with an initial type environment. This type environment is passed down recursively through the various nodes of the abstract syntax tree until we hit the leaves. And starting at the leaves, we use the environment to compute the types of each sub-expression, working our way back up the tree to the root. Let's start our discussion of the implementation of cool type checking with one of the simpler rules in the type system, the rule for addition. And let's just briefly review what this rule says. It says that the type check E1 plus E2, we first have to type check E1, and then we have to type check the sub-expression E2. And both of those sub-expressions have to have type int. And if they do, then we can conclude that the overall expression, the sum of the two sub-expressions, also has type int. And furthermore, this type checking is carried out in some environment. In this case, the environment is the same for the entire expression and both sub-expressions. Just to remind you, there's always an object environment for the object names in scope, a method environment for the methods of the various classes, and we always need to know the current class. Now, how would we implement this? Well, we're going to have a recursive function called typecheck that takes two arguments. It takes a type environment, and this will be a record. I'm not specifying exactly how that record is declared, but I mean, essentially it's going to have three parts, O, M, and C. And it also takes an expression. And so here we're just doing the case where the expression is E1 plus E2. And what should the code look like? Well, we can pretty much just read the rule and translate directly into code. And this is one of the nice things about the notation for type systems, is it really tells you very, very clearly how to write the implementation from the description. So what's the first thing we have to do? Well, we have to type check the sub-expression E1. And we can see from the rule that the environment in which E1 is type checked is exactly the same as the environment of E1 plus E2. So we just pass whatever our original environment argument was for E1 plus E2. We pass that argument on to a recursive call to type check the sub-expression E1. And that type checking will run, and it will return some type T1. Now, we don't know that T1 is an integer at this point. We're going to have to check that. So we just remember what the type of E1 is. And furthermore, we type check E2. Okay? And that also happens in the same environment. We can see that here in the rule. And again, we'll get back some type for E2, so type T2. And then we confirm that both T1 and T2 are type integer. Now, we could have done the check that T1 is int right away, right after we had type checked T1. And that would have been a fine thing to do. Here, just to save space on the slide, I've put the checks for T1 and T2 all on one line. And if that check succeeds, if it doesn't succeed, presumably there should be some code in here to print out an error message. But if both T1 and T2 are in fact integers, then the type of the whole expression is also an integer. So that's what's returned by this call, by the outermost call here to the type check function. So now let's take a look at a somewhat more complex type checking rule and its implementation. Here's the rule for let with initialization. So we're declaring a variable x of type t, and that's going to be visible in the expression E1. But before we execute E1, we're going to initialize x to the value of E0. And then after we've evaluated the entire let expression, we expect to get back something of type T1. And now for all of that to work out, a few things have to be satisfied, and those are listed as premises here of the rule. First of all, E0 has to have some type T0, which is a subtype of T. And that's to guarantee that this initialization is correct, that X can actually hold something of E0's type. And for the entire expression to have type T1, well then E1 has to have type T1. But that type checking is carried out in an environment that's extended with the declaration for X. And so we also know within E1 that X has type T. So now let's write the type checking case for this. So the function type check is, again, it's going to take an environment as argument, and now we're doing the case for let with initialization. So just reading off the rules and what the conditions are that we have to check, we can see that one of the first things we have to do, or one of the things we have to do, is to check that E0 has some type T0. So we just have a recursive call to type check here. This is carried out in the same environment as the overall expression. So we just pass the environment on to the recursive call, and now we're just type checking E0 and we record its type T0. So the second premise is implemented like this. Now we're type checking E1, and we expect it to have some type T1. But now the environment is different. So we're taking the original environment, the overall environment of the expression, and we're adding a declaration that X has type T to that environment. So we're extending the environment with an additional variable declaration. Okay, so we do that type checking call, and we get back a type T1. Now we have to check that T0 is a subtype of T, so that's a call to some function that implements the subtyping relationship. And if that passes, if that check passes, well, then we're done, and we can return the type T1. And there's a little mistake here on the slide. There shouldn't be a semicolon there. So we just return T1 as the type of the entire expression.